Okay, guys. Okay, so let us now try to figure out some of the structure of a group of order 60. If you're wondering, this is kind of like following, if you happen to have the textbook Dummett and Foote, let me tell you where this comes from. Okay, this is like section 4.5 in the book. I think it's called Abstract Algebra. By Dummett and Foote. Okay. The proofs were not from that book, but this example is from that book. And what we want to do is so example, let G be a group of order 60, and suppose that the number of subgroups of order 5, or sorry, the number of Sylow 5 subgroups, oh yeah, I call that capital N, is not equal to 1, then G is a simple group. Meaning that, okay, let's just unravel what this is saying. If it has more than one Sylow 5 subgroup, then it has no non-trivial normal subgroups. Okay, so let me remind you what simple means. G is simple means that if H is a normal subgroup of G, then H is trivial, or H equals G. Okay, so these groups are pretty special. Normally we have maybe like a bunch of normal subgroups. For example, we saw that in a group of order 30, we have a normal subgroup of order 15. But now I'm saying that, okay, so that's what simple means. Notice that if N5 equals 1, then that means a Sylow 5 subgroup would be normal. Okay. Okay, and now we're saying if there's more than one Sylow 5 subgroup, that forces G to have no normal subgroups, well, except for the trivial subgroup and the whole thing. Okay. So let's try and work out this example. First, let's see the conditions that are forced upon us for N5. So you have to factorize 60. So that's not too bad. 60, that's just 4 times 3 times 5, so it's 2 squared times 3 times 5. Just for safety, let's write out the conditions on N3, N5, and N2, just for practice. So N5 is congruent to 1 mod 5, and N5 divides 3 times 4, divides 12. Okay. So what that means is N5 can be 1, 6, 11, 16, and so on. And which of those divide 12? Well, 1 and 6. Those are the only divisors of 12. Okay, so this tells us, Sylow theorem tells us that N5 is either equal to 1 or 6. Okay, what about, let's just go through the motions. N3 is congruent to 1 mod 3. N3 divides 4 times 5, which is 20. Okay, so the possibilities for N3 are 1, 4, 7, 10, 13, 16, 19, 20. Well, you have 1, 4, 10. Okay, what about N2? Well, N2 is congruent to 1 mod 2. In other words, N2 is odd, and N2 divides 15, which means N2 can be 1, 3, 5, or 15. Okay, so that is all the arithmetic stuff that the Sylow theorems tell us. And then in this example, we're assuming that N5 is not 1, so we can assume that N5 equals 6. Okay, so in our case, N5 is not equal to 1 by hypothesis, so N5 equals 6. Okay, for a contradiction, we want to show that there's no normal subgroups. Let's just let H be a normal subgroup of G. And the contradiction part is assuming that H is not equal to the trivial subgroup and H is not equal to G. Okay. And we're trying to show H doesn't exist. Okay. Okay, so what do we do? Okay, so we know that the number of conjugates of a Sylow 5 subgroup is 6. That means what it tells us is that the index, so let's take let P be a Sylow 5 subgroup. And if we look at the index in G of the normalizer of P, that is the number of conjugates of P, which is 6. Okay. That tells us, well, G has 60 elements. 60 divided by the order of the normalizer is 6. So this order of the normalizer has to be 10. Okay. So G has a subgroup of order 10. Okay. Now, according to the text, we should now think about whether 5 divides the order of H or not. Well, I mean, we could think of anything that works, I guess, but probably let's stick with something that works. Okay. So one case is that 5 divides the order of our normal subgroup H. Okay. What does that tell us? Then H contains a subgroup of order 5. Okay. Now a subgroup of order 5 has to be a Sylow 5 subgroup of G. Because the Sylow 5 subgroups of G all have order 5. This subgroup of order 5 has to be one of them. You can, like, why does H contain a subgroup of order 5? Well, again, that's by Sylow theorems again. Okay. Okay, now we know all the Sylow 5 subgroups are conjugate to P. So there's GP, G inverse is a subset of H. Okay, so P is contained in G inverse H G. We multiply on the left by G inverse, multiply on the right by G, we get this. Okay, but H is a normal subgroup of G, so G inverse HG is just equal to H. So P is a subgroup of H, and in fact, all the CLOP 5 subgroups are contained in H. So we can say like, so KP, K inverse is contained in KH, K inverse, which equals H for all K. All the CLOP 5 subgroups are conjugate to P, so H contains all the CLOP 5 subgroups. Okay. Now, what does that tell us? Now we think back when we were talking about the Sylow 5, the Sylow theorems, we could use counting to try and figure out like some contradictions, right? So that's what we're going to do now. There are 6 Sylow 5 subgroups. And in each of them, you have the identity element and then 4 elements of order 5, and they are all disjoint except for the identity. Okay. So you have 4 times 6 elements of order 5 plus identity element. And these elements are all elements of H. So this has to be less than or equal to the number of elements of H. Okay. So we're taking the 4 non-identity elements of each CLOP 5 subgroup. There's 6 different CLOP 5 subgroups. And then the identity, which is common to all of the CLOP 5 subgroups, and that is a lower bound for the number of elements of H. Okay, and this is 25. So H is at least 25. Okay. H is a subgroup of G, so H divides 60. So what possibilities are there for H which divides 60 and are less than 25? So that implies that either H equals 30 or H equals 60. Okay. If H equals 30, what happens? Well, then H has a unique subgroup of order 15. And then that contains a unique subgroup of order 5. A unique normal. Right? Because we know that like groups of order 15 are cyclic, and that is what allows us to conclude that this has a unique subgroup of order 5. And now there is supposed to be 6 subgroups of order 5, but we only find 1 here. Okay, so this would imply a contradiction. Since N5 equals 6. Okay, so therefore the number of elements of H has to be 60. In other words, H was not a proper subgroup. and that implies H equals G. Okay, so if H is a normal subgroup of G and 5 divides H, then H equals G. Okay, so the other case is that 5 does not divide H, the order of H. Okay, well then the order of H has to divide 12. So it can be 1, 2, 3, 4, see 6 or 12. Okay. So what happens? I guess in the textbook they use some like tricks and stuff, but let's just try and go through this case by case. If H equals 2, and look at G bar, which is G mod H. Okay, G bar is a subgroup of order 30. There's a group of order 30. The order of G bar is just 60 divided by 2, which is 30. G bar, we know that any group of order 30 has a subgroup of order 15, which is normal. So H bar, subgroup of, or sorry, I shouldn't say H bar, I should say K bar, which is a subgroup of G bar, has order 15. And now a subgroup of G mod H is a subgroup of G which contains H. So there exists K, which contains H, and it's contained in G, such that K mod H equals K bar. Now, K bar has order 15, so K, order of K divided by 2 equals 15, so order of K 30. Okay, so if G has a subgroup of order 2, then G has a subgroup of order 30. This subgroup of order 30 is index 2 in G, it's automatically normal. But we already saw that if K has a normal subgroup of order 30, that's a contradiction to N5 equals 6. Oh, can I move it to the left? Sorry about that. Yes, I will. Okay. We already saw how you can't have any subgroups of order 30 in this situation. We found one of order 30. Okay. What about if H equals 3? Okay. Then we still let G bar equals G mod H. Then G bar has order 20. Okay, let's try and think about the Sylow of 5 subgroups of G bar, right? Sylow theorems for G bar. What do they say? Well, they say that I'll use like n prime instead of n. So it says that n5 prime is congruent to 1 mod 5, and n5 prime, so 5 prime divides 4. And now the only divisor of 4, which is congruent to 1 mod 5, is 1. So n5 prime equals 1. So now G bar has a normal Sylow 5 subgroup. So there exists K bar in G bar such that the order of K equals 5. And now writing K bar equals K mod H, K turns out to be a normal subgroup of G of order 15. Okay, so now K bar is normal in G bar. K bar has 5 elements. So if I write k bar equals k mod h, then k is normal in G, and k has the number, so it has the index of k and h times number of elements of h. Okay, h has 3 elements. This index has 5 elements. As 5, you get 5 times 3 is 15. So in this case, G has a normal subgroup of order 15. We just saw that that can't happen in the previous part. So K is normal in G. K has 15 elements. This is impossible. This contradicts. And 5 equals 6 again, because 5 divides the order of a normal subgroup of G. Okay. So we did 3. Next would be 4, 6, and 12. What about the order of H equals 12, or sorry, equals 4? And our strategy is the same. We let G bar be G mod H. G bar has 15 elements. Okay, G bar we know has so we know G bar is cyclic of order 15, as all groups of order 15 are cyclic. We know that from Sylow theorems the first time. Okay, so G bar is abelian, so all its subgroups are normal. In particular, it has a subgroup of order 5, which is normal. So take K bar contained in G bar to have 5 elements, and K bar is normal in G bar. And writing K bar equals K mod H gives K normal in G, and K has 5 times 4 equals 20 elements. But we already saw a normal subgroup with order divisible by 5 is a contradiction. This is a contradiction again. So all of these basically come down to the same thing, that you aren't allowed to have normal subgroups of order divisible by 5 if n5 equals 6. Okay, there's 2 more things to do. The case that H equals 6, then we let G bar be G mod H. G bar has 10 elements. Okay. Now the groups of order 10, you can use the Sylow theorems again. So again, I'll use n5 prime for the Sylow theorems for G bar. n5 divides 2 and is congruent to 1 mod 5. Okay, which tells us that n5 prime equals 1. Now, so we can take K bar to be a normal subgroup of G bar, and K bar has order 5. Now, that means that writing K bar equals K mod H, order of K is just 6 times 5, which is 30, and K is normal in G since K bar is normal in G bar. Okay, again, this is a contradiction. Okay. And then the last case is that H equals 12. H has order 12. Well, then we do G bar equals G mod H. Okay. G bar has order 5. Okay, now this is a little bit different, but we can't just take a Sylow subgroup of G bar, because that would be the whole group. Okay, but we do have, let's try and find a different normal subgroup of H. Right, so let's use the Sylow subgroups for H. So 12 is just 4 times 3. Let's prove this lemma. If H has order 12, then there exists a normal subgroup of H either of order, yeah, let's just prove this. Okay, and let's see what that tells us. Proof. Well, we look at the Sylow 2 subgroups and the Sylow 3 subgroups. Right, N3 prime is congruent to 1 mod 3, and 3 prime divides 4. Again, 12 is just 3 times 4. This tells us that N3 prime equals 1 or 4. Okay, what about N2 prime? N2 prime is odd. And N2 prime divides 3. So N2 prime equals 1 or 3. Okay, now let's combine. So we want to say that either this is 1 or this is 1. Okay. So let's try and find a contradiction if they're both, if N3 prime is 4 and N2 prime is 3. Okay, and again, we use the same trick. We try and count the number of elements of order 3. There are 4 Sylow 3 subgroups. Each contains 2 non-identity elements and plus the identity. So from here we have 2 times 4 Sylow subgroups. These are elements of order 3. Okay. Now there are, so this is 8. That means that there's 4 elements left over, which can possibly be in the Sylow 2 subgroups. So to contribute to the Sylow 2 subgroups, but a Sylow 2 subgroup has to have 4 elements. And there's only 4 to go around. Okay, so there can only be one Sylow 2 subgroup. Because a Sylow 2 subgroup has 4 elements, and it can only be the 4 elements that are not of order 3. Okay. So if there's one Sylow 2 subgroup, then N2 prime equals 1, and we have a normal subgroup. And then the other possibility is that N3 prime equals 1, which means we have a normal Sylow 3 subgroup. Okay. So what we've shown is that if H has 12 elements, it either has a normal Sylow 4 subgroup, a normal subgroup of order 4, or a normal subgroup of order 3. Okay, so finally, let's do our last step in a group to figure out the groups of order 60. Let's show. So we have a normal subgroup K in H, where order of K equals 3 or 4. And let's show that K is also normal in G. Okay, And then our conditions, our hypotheses are that we're in this assumption that H has 12 elements and H is normal in G. And let's show that K is normal in G. So first, so we're trying to show this. First of all, K is either a Sylow 3 or 4 subgroup of G. Because Sylow 3 subgroups have order 3, Sylow 4 subgroups have order 4 in G. So, and K has either that or that order. Okay, so, oops, sorry, not, yeah. This K is either a Sylow 3 subgroup or a Sylow 4 subgroup. Okay, all the Sylow 3 subgroups and 4, like in either case, all the subgroups of that type are conjugate in G. Okay, so let G be in G, then GK, G inverse is also a Sylow, I'll just say subgroup of G, of the same order as K. Not only that, but GK, G inverse is contained in GH, G inverse. Because K is contained in H, GK, G inverse is contained in GH, G inverse. Okay. But GH, G inverse is just H, since H is normal. Okay, so now GK, G inverse is a Sylow subgroup of H. Okay, but K is, but our whole thing in the last lemma was that K is coming from, K is normal in H, so K is the unique Sylow subgroup of H of that order. Okay, so now either N3 prime equals 1 or N4 prime equals 1. So basically, if K is a Sylow 3 subgroup, then N3 prime equals 1, and GKG inverse, that's another Sylow 3 subgroup of H, but there's only one, so so it tells us that GKG inverse equals K. In other words, K is actually normal in G now. K is normal in G, and now we have shown that if G has a subgroup of order 12, it has a subgroup of order either 3 or 4, and that reduces us to previous work, you know, where we figured out that G can't have any subgroups of order 3 or 4. That leads to like contradictions. So K has order 3 or 4. K is normal in G is a contradiction again. Okay, and therefore that eliminates all the possibilities for orders of normal subgroups. So G has no normal subgroups. Except just a trivial one and G. And that's the end of the proof. And this was all done assuming that the number of Sylow 5 subgroups is not equal to 1. That's the only thing we were working with. And then as a nice corollary, what we get is this corollary. So theorem, I guess this is a corollary, not a theorem. Sorry about that. So the order of the alternating group with 5 elements. So that's just the order of the symmetric group on 5 elements divided by 2. That's just 5 factorial over 2. That's 60. And A5 has more than one Sylow 5 subgroup. And then just from that statement, A5 is a simple group. Okay, so it's a group of order 60. So sorry, it tells us that A5 is a simple group. Okay. And the proof of that, we have just take like 1, 2, 3, 4, 5. Take that to be, take the subgroup generated by a 5 cycle, call that H1. Okay, the elements are, you have 1, 2, 3, 4, 5. You have 1, 3, 5, 2, 4. You have 1, 4, 2, 5, 3. And then you have 5, 4, 3, 2, 1. Okay. Taking like, so this 5 cycle is an even permutation. It's an element of the alternating group with on 5 things. Okay. This 5 cycle generates this subgroup H1, which has 5 elements. Subgroups with 5 elements are Sylow 5 subgroups of A5. Now, just write down a different 5 cycle than these 4, and you get a different Sylow 5 subgroup.